Okay, as we continue with our constructions, I do recommend that if you have a printer, you have the opportunity to download the template from which we're going to do some notes together. So if you do not have a printer, that's fine, but you'll notice that I've already sort of set up some of our constructions together so that you can just go along as we go along. But of course, we will be writing them out as well. All right. So what we are going to look at today is we're going to continue with some constructions, and I'll be able to reiterate some of what we talked about the other day when we started constructions in 12.2. So one of the things I want to start with is a definition of what are called concurrent lines, because we will be talking about lines a lot and line segments. So concurrent lines, okay, are basically lines which intersect at a point. And we call that point the point of concurrency. So anytime two points intersect, that point of intersection is called the point of concurrency. Okay? Now, as we start our constructions, we're first going to learn how to construct parallel lines. And we're going to do this in two different ways. Okay? So let me erase this so that I can kind of put them next to each other. So our first construction is parallel lines. All right. We're going to do two different methods. First one's called the rhombus method. And what we're going to do is we're actually going to construct a rhombus. Okay? And let's think about what a rhombus is. A rhombus has four sides. Opposite sides are parallel and congruent. Okay? So let's think about this. Opposite sides are parallel and congruent. And in the last section, we talked about how to copy a segment. Well, that would keep them congruent. So let's start with this. Let's start with our line. So in our first example, on that template, I gave you a line. And I gave you a point not on the line. So what we want to do is we want to construct a line parallel to this line. So I'm just going to create a point. I'm just going to call this point P. You can choose that point to be anywhere. And what I want to do is I want to construct a rhombus. A rhombus has congruent sides. So the first thing I'm going to do is I'm going to choose a corner or a vertex for my rhombus. So actually, I want to do this with my construction tools. I'm going to choose this point right here. I don't want to put it on the black because it'll just make everything super messy. So I'm going to call this point point A. So what I want to do is I want to copy this line segment from A to P. So I'm going to open my compass up. I should go grab a compass. I chose to create a compass. I'm going to open my compass up from A to P. And I'm going to swing an arc from A to P that is going to be the same as the arc onto my line segment. So now I know that these distances are identical. Without changing it, I'm going to go to each one of these vertices. I'm going to swing an arc. Without changing my compass, I'm going to swing an arc. So technically, all 4 of these sides should be the same length. I'm going to do it again. First thing I did was I took my compass. I'm trying not to get my hand out of the way. And I figured out how long it was from A to P. I made that distance the same over here. And then from each one of those corners or vertices, I swung an arc, and I swung an arc. And what we have created now, I have a line segment going through the 2 points. And if I connect that vertex with our point of intersection, and if I connect that point of intersection with our other point of where we swung the arc, should notice that when, I'll do it again, when I opened up this compass, this certain distance, I'm going to go grab my other compass so you guys can see it better. Hang on, let me pause for a second. All right, so when you have your compass and you open your compass up from A to P, and I swing that compass around, it's going to make a mark. Then, without changing your compass, swing an arc from each of these vertices, this vertex and this vertex, and they have a point of intersection. And now when you measure, this line segment is the same as this line segment, which is the same as this line segment and this line segment. So opposite sides are congruent and opposite sides are parallel. So we have now constructed parallel lines. So our new line is now parallel with our constructed line. So this is called the rhombus method because we created a rhombus. Now, if you don't like that method, we can also do this by doing corresponding angles, because we have talked about parallel lines being cut by a transversal. So let's do this through corresponding angles. Because if you recall from last chapter, corresponding angles are congruent. If 2 corresponding angles are congruent, then the lines are parallel. So let's start with our given line again. And we'll start with our given point again. I'm going to try to make them about the same. So it looks like it's about right here. But this time, I'm going to construct corresponding angles. Okay? Because if 2 corresponding angles are congruent, then the lines are parallel. So in this case, I want to copy an angle. I want to construct an angle. So first thing I have to do is I have to have an angle. So I'm going to take, and again, I'm going to pick some point along our line, and I'm going to call this point, for our purposes, A. And the first thing I'm going to do is I am going to create what will ultimately become the transversal. It will be the line that passes through the other 2 lines. And what I want to do is, if I can create a parallel line right here, I know that this angle right here would correspond to the angle right up above it. And if those are congruent, then the lines must be parallel. So I'm going to copy a line. I'm going to copy an angle. So we're going to copy an angle. All right, we did that last section, so let's try it again, okay? So in order to copy the angle, let's first figure out how far we would like to go. Meaning, if this is our point from here to here, that distance, I'm just going to bring this all the way down. So right now I know those segments are the same length. Okay? And now what I want to do is I want to make sure I copy that line segment. So what I'm going to do is, since I know this is the distance we have, I'm going to bring it, slide it straight up. So see, I've now just gone straight up. And if you recall, when we copied an angle, we needed to know how wide it was. So I'm going to go from one vertex to the other. And I'm going to go from one vertex to the other. Okay, I need to extend my line a little bit. That happens when you're constructing. Don't ever erase construction marks. So what we've done is we have, let's do it again. I want to know how large this angle is, so I'm just going to make a line segment, line segment. To copy an angle, we now figure out how wide to open it. So I have to copy this down here. That's what I'm going to do from the other side up here. And now when I copy this angle, I'm copying this angle to right here. And when I do that, I can connect my X's here, connect my points of intersection, and I have created corresponding angles by copying the angle. All right, so we copied it just like we did before. We just copied it into space and then ended up creating the other line segment. And now we end up with, again, parallel lines by copying an angle. By copying an angle, we created corresponding angles. Okay. So the rhombus method in your notes, a quadrilateral with 4 congruent sides where opposite sides are parallel and congruent. So that's what would go on that line, this line up here that I'm talking about. For the corresponding angles method, okay, if, I always want an if-then statement, if 2 corresponding angles are congruent, then the lines are parallel. So that gives you 2 different choices on how to construct parallel lines. All right? And now what we want to do is we want to practice a construction we did last section, and we want to see how that can help us with some triangles. So I'd like to do a recollection and recall how to construct an angle bisector. So this will piggyback off of, or this will scaffold from, springboard from, bisecting an angle. So let's first recall and do the construction of an angle bisector again. All right, let's do an angle bisector construction. See if you can remember from last section. And then we'll take a look at some properties or theorems regarding some angle bisectors. So let's first start with an angle. Any angle. And the one I gave you, if you're using that template, I gave you an angle that looks roughly like this. Okay? So if you're using the template, we're just on the second page there. All right, so let's bisect that angle before we start looking at what happens when we bisect all three angles of a triangle. In order to do an angle bisector, we're first going to open our compass up. It does not matter how far. You're going to open your compass up and swing an arc that will intersect both sides. So I'm going to open my compass up. I'm going to swing an arc. Now, from each of those points of intersection, you can keep the distance the same or not. It does not matter. I'm going to come out here into the interior part of the angle and create an arc and do the same thing from the other point of intersection. They should overlap. And when they overlap, and you connect that to the vertex of your angle, I think mine slipped a little bit, slipped a little bit, you should get an angle bisector. Okay? So that angle bisector, now we have that, excuse me, I want to talk about all the points that are along the bisector. So we did this construction in the last section, but we really didn't talk much about the angle bisector theorem. All right, so let's write that down now. We have what's called the angle bisector theorem. So this is a law that has been proven about any point along the angle bisector. There's two things we want to talk about. Any point P that's on an angle bisector is equidistant from the sides of the angle. Okay? Any point P, we'll just call it on an angle bisector, is equidistant from the sides of the angle. All right. Now, keeping in mind that the shortest distance from a point to a line is perpendicular, okay? So if I pick any point on this angle bisector, I always want to go perpendicular to the other side. The shortest distance between any two points is a line which is perpendicular. So the shortest distance would be this perpendicular line right here. And I guarantee you that distance will be the exact same distance as the perpendicular line segment, the shortest distance going the other direction. That's what it's saying. Any point along that perpendicular bisector will be equidistant. These two lengths are congruent, right? And we talked about how to create a perpendicular the other night, but you can notice those are congruent. They're the same length. And conversely, any point on the interior of an angle, so any point on the interior of an angle that is perpendicular to from the two sides lies on the angle bisector. Okay. So any point, make sure you put on the interior of an angle any point on the interior of an angle, which is equidistant from the side, from both sides, or the sides, I'll say both, is on the angle bisector. All right. So as soon as you find that it's equidistant from both sides, it's got to lie on the angle bisector. And that's called the angle bisector theorem. So what we want to practice is we want to take, and given the triangle that I gave you, if you have the template, if not, we'll draw a triangle. We want to find, and we want to bisect all three angles and take a look at what happens when you bisect all three angles. All right, so let's do that. Let's do a construction. And let us construct the angle bisectors of a triangle. So the first thing I'm going to do is I am going to sketch a triangle, and we'll call it triangle ABC. It gets kind of slippery on this whiteboard, so I do apologize for things slipping. It's a little bit easier with a compass, a pencil, and paper, where that compass can really kind of grip into the paper. It slides off the whiteboard, so I will do my best not to have it slide. And we called this triangle in those notes ABC. So let's construct three angle bisectors. So we're going to practice this 3 different times. So I am going to swing an arc. An arc. From each of those, I'm going to make it out here so it doesn't get in my way. Swing an arc, swing an arc, so it didn't intersect, so I go back to it. And I am going to bisect angle A first. Find those 2 points. Oh, it's sliding around a lot. So here's an angle bisector. I'm going to do it again for angle B. For angle B, I need to swing an arc, come out from each of them the same, or a distance. I chose not to open my compass up anymore. From that point of intersection to vertex B, should be my angle bisector. Never erase construction marks. Just leave them on your paper. If they run into words or other problems, leave them alone. And then I'm going to do the same thing with angle C. This one's a little harder because I'm right-handed. So I will do my best. Go angle C, swing an arc, come out here. Swing an arc, swing an arc. Connect this to vertex C. And what you'll notice is all 3 of those lines are concurrent. They are 3 lines which intersect. So all 3 of these angle bisectors intersect at a point of concurrency. Okay? So I'm going to call that point P. the angle bisectors. Right? So I asked you, well, let's see, what do you notice? What we notice is that whenever you have three angle bisectors, they will intersect at a point of concurrency. Okay? So that's what we notice. So on this question here, what do you notice? We notice that all three angle bisectors intersect at a point inside the triangle. All three angle bisectors intersect at a point, we called it P, okay, inside the triangle. Do we have a point of concurrency? Yes. Well, we already defined a point of concurrency. That is the intersection of two or more lines. Okay? So we already did that definition. And then we have what's called the incenter. And that is the point of intersection of the angle bisectors. So take a look at the word, in-center. Kind of tells you that it's on the inside. So this is the point of concurrency of the angle bisectors of a triangle. Now, just a little side note, okay? A little side note. We talked earlier that if a point is on an angle bisector, it's perpendicular to the three sides. Okay? So, watch what's going to happen here. We know that it's perpendicular to the three sides. So, I know that the shortest distance between this incenter and this side, the shortest distance is perpendicular. Okay, so this shortest distance, and I could create a perpendicular bisector. But what I want to show you is, if the shortest distance from that point to that side is the same, I should be able to draw a circle within this triangle. So try that with your compass, okay? We know that the incenter is the center of all these points of concurrency. We know that if this point lies on an angle bisector, it's perpendicular to the side, which means it's perpendicular to all three sides. So what you'll notice is, I can take, this is going to be hard on a whiteboard, I can take and I can draw a circle. Oh, sorry, my finger's slipping. This is so hard to do on a whiteboard. So much easier in a classroom. If I put this circle all the way around, I missed it on this one, it will intersect at 3 points on the circle. All right? I can always put a circle, and I can put a circle, an inscribed circle inside this triangle. So I have inscribed a circle. Note, we have inscribe a circle. So this circle's on the inside of the circle. Okay, this has a center located at the incenter. We know that the radius of the circle is the shortest distance from the incenter to the sides of the triangle. Oops, sorry, didn't know I was off the board. Squeeze it in here, I'll say it again. It's the shortest distance from the incenter to the sides of the triangle. To the sides of the triangle. So if I can find the incenter, I can inscribe that circle. And then on those notes, I talk about a point of tangency. Okay? A tangent line touches a circle at one point. So each of these sides would become what's called the tangent line. And each of these points would be a point of tangency. Okay. So we looked at what happens if we bisect the angles. Now let's look at what happens if we bisect the sides of a triangle. So the first we did angle constructions and bisecting an angle and noticing what happens when we do that for all three vertices. Now let's go back and instead bisect the sides. So this is a recap from section 2. Let's do a perpendicular bisector. You can grab your notes, but we're going to do it again. We're going to first practice the bisector from last section. And then we're going to do it 3 more times. Okay. So let's first recollect how to construct a perpendicular bisector. Okay. Here we'll even go farther of a line segment. If I bisect something, that means I cut it in half, 2 equal segments. If we have 2 equal segments, this will allow us the opportunity to find a midpoint, because if it bisects it, it creates 2 different congruent pieces. And then it'll also allow us to construct a right angle. Because by definition of perpendicular are 2 lines or line segments which intersect to form a right angle or 90 degrees. Okay, so let's first just practice mechanically how to do that construction. So if I give you a line segment, whoops, slipped a little bit. I'm going to call this line segment, segment AB. And I believe that's what I called it. Hang on, let me turn the page on what you guys have. Oh, I didn't label it. So if you choose to, I just chose to call it AB. You don't have to. Okay. Our goal is to find the midpoint. If I want to find the midpoint, I'm going to construct a perpendicular bisector. So to go through that again, I'm going to take my compass, and the first thing I want to make sure of is that I open the compass past what I would think halfway is. So notice I'm going to open this compass up way farther than halfway. I'm not going to try to judge halfway. I'm just going to open it up more than halfway, so that no matter what, I know I'm farther than halfway. And then I'm going to swing an arc that's the same distance from both of these endpoints. Okay? So if I take my compass, I open my compass up past halfway, I swing an arc. Now you can either keep it congruent, keep it going or not. Keep that same measurement, swing an arc. And what you'll notice is when you combine these together through those points of intersection, you have created a line, which if I grab my protractor, should be pretty spot on. That's pretty close to 90 degrees. I'm off by just a hair. Okay, it's probably from the slipping. Okay, so we have constructed a perpendicular bisector. Because it's a bisector, we now have two pieces of information. We now have that we have a midpoint. I'm going to call M the midpoint. And we also have that we have created a right angle. So if you're ever asked to find a midpoint, just do a perpendicular bisector. If you're ever asked to construct perpendicular lines, just create a perpendicular bisector. So now we want to do that on a triangle. We want to construct the perpendicular bisectors of a triangle. So I gave you a triangle if you printed that out, or start with any triangle. Just try to leave yourself room to make construction marks. It does not have to be equilateral. I gave you triangle ABC. All right, so mine looks a little different than yours on that paper, but does not matter. It can be an acute triangle, it can be obtuse, it can be scalene, isosceles, equilateral. I called this triangle ABC. And in my opinion, it's easier on paper because you can move the paper around. Our whiteboard is fixed here to the pool table, so I can't really move it. So I'm going to first do a perpendicular bisector of line segment. I'll do AC first, since it looks a lot like this one. So I open my compass up more than halfway, and I'm going to swing an arc outside on both sides of this line. And I have to move, uh-oh, my finger slipped. So let me open this up. There we go. There we go. Out here. And again, being right-handed on a board that doesn't move. Let me see if I can do this left-handed. Okay. And if I connect these, point of intersection, I should have my midpoint right here, and I now know that's a right angle. I'm going to do the same thing with side length AB. String an arc out here, out here, out here. How am I going to do that? I might need to ask a little forgiveness since I cannot spin around. There's my second. Oh, it's not too bad. Those should be equidistant. Those should be a midpoint. That's perpendicular. I do it one more time with line segment BC. String an arc. String an arc. String an arc. An arc, uh-oh. Gotta keep this one going farther so it hits. Okay. And in a perfect world, I should get 3 concurrent lines again. Mine slipped a little bit. Not too bad, but a little bit. I have a right angle, and sure enough, I have a point of concurrency. All right, so I have a point of concurrency again. So let's make some observations. And if I take a look and make a note of what we may have noticed, what do we notice? Well, all 3 perpendicular bisectors intersect inside the triangle again. All 3 perpendicular inside the triangle. In this case, because it's an acute triangle. We may end up seeing what happens if it's not acute. Okay? So that point of concurrency is inside. We will always have a point of concurrency. All right? Now, we have a name for that point of concurrency. This time it's called the circumcenter. So the circumcenter is the point of concurrency of perpendicular bisectors. And what we'll find is we have a perpendicular bisector theorem. And what we'll notice is any point that is on a perpendicular bisector ends up being equidistant from the vertices. That point of concurrency. Okay? So the point of concurrency, the circumcenter, is equidistant from each vertex of the triangle. So in our case, we could say the distance from A to P is congruent to the distance from P to B, which is congruent to the distance from P to C. So all three of those are congruent. Well, if all three of those are congruent, they create a radius, which means that I can circumscribe a circle around this triangle. Since all three of these are the same, all three of these become radii. These are all radii, plural of radius. They are the radii of a circumscribed circle about the triangle. So this time we're going to have a circle on the outside of the triangle. So since all these distances are the same, since P to C, and if I open up my compass, here I'll do it with this compass. Since P to A is the same as P to B, which is the same as P to C, that means those are all the radii of a circle. And if I construct a circle all the way around, okay, each of those vertices will and should, especially on paper, because it's not going to slip like mine is, I should be able to construct, and I'll try my best. Let's see if I can do this pretty well. If I start with this one, it ran out a little bit. It should come around, and I do apologize that this did not match up perfectly. I'm trying to do it left-handed. Your compass will probably work better than mine. We end up with a circle that is circumscribed about the triangle. So the in-center was inscribed. The circumcenter circumscribes. Those are on the outside. All right? And we'll investigate a little bit more with this with our lab that we're going to do. Okay? So try to do some of these constructions. It's easiest if you have sharp pencils, a tight compass that doesn't slide, and paper so that the compass can grip. And I appreciate your understanding that this is very slippery. So when we get back together, we'll practice this in a lab situation. And until next time.